Hi guys, welcome to Easy Math.
In this video, we are going to discuss about the definition quotient group and the theorem associated with this. Okay, let G be a group and N be a normal subgroup of G. That means a group G, let us take a group G and N be the normal subgroup of that group G. Then the quotient group G over N is defined as the set of all right cosets of N in G. That means G over N is defined as the set of all right cosets. We know that the set of all right cosets can be written as NA. Okay, therefore G over N can be written as set of all NA such that A belongs to G. This NA is the right coset of A in G. Now let us see this theorem. Let N be a normal subgroup of a group G. Then G over N is a group under the operation divided by NaNb is equal to Nab. Normal multiplication, right? Let N be a normal subgroup of G. Then you have to prove that G over N, the quotient group, is a group. That means you have to prove 4 conditions: closure, associative, identity and inverse. Closure property. It means let us take 2 elements from this quotient group, that is NA and NB, because the elements in this quotient group are in the form of right cosets, right? Therefore, we are choosing 2 right cosets from the quotient group G over N. For all these 2 elements, right cosets of that elements A and B belongs to the group G. Now, NA and B can be defined as the normal multiplication, that is NAB. Here, A and B belongs to G. G is a group. Therefore, it satisfies the closure property, right? AB belongs to G. Hence, this NAB belongs to G over N. Therefore, NA into NB belongs to G over N. Second one is the associative condition. Associative condition means let us take 3 elements from the quotient group G over N. Now we have to prove that the NA into NB into NC is equal to NA into NB into NC. For that, let us take the left hand side, NA into NB into NC. This NA NB can be written as NAB. Therefore, this can be written as NAB into NC. This can be written as NAB into NC. That means this can be written as NABC. This can be written as NA. You have to interchange the bracket, that is NA into BC. This BC can be written as NA into NBC. Therefore, you have to take this as NB into NC. This is the LHS, hence G over N is associative, right? Now the third condition, existence of identity. For that, we have choose that element NE. NE means N, right? This is the right coset. Therefore, this element belongs to the quotient group G over N. For all E belongs to G. Since G is a group, E is the identity element in that group G. Now, for that identity property, you have to prove that NA, NE is equal to NA and NE, NA is also equal to NA, right? Therefore, first condition NA into NE, that is NAE. AE means you are getting A. Therefore, NA, NE is equal to NA, and similarly we can prove that NE, NA is also equal to NEA, that is NA. Hence, NA, NE is equal to NA, which is equal to NE, NA. Therefore, NE is the identity element of G over N. Next, fourth condition is the inverse property. That is, let NA belongs to G over N, where A belongs to G. Since A belongs to G, G is a group, inverse element exists, that is A inverse belongs to G. Hence, NA inverse belongs to the quotient group G over N. Now, NA into NA inverse can be written as NAA inverse. AA inverse is equal to E, we know that. Also, similar case, NA inverse into NA is equal to NA inverse A. The value of A inverse A is also E. NA inverse is equal to NE, which is equal to NA inverse NA. Hence, NA is the inverse element of NA. Therefore, G over N is a group. Since G over N satisfies the closure property, associative property, identity property and inverse property. Hence, G over N is a group. Hence, the theorem.
Thank you for watching. Don't forget to like, share and subscribe. Bye guys.